Inductance of transmission lines. Here we will discuss the theory behind and later on show some calculations, okay, of the inductance due to internal flux and internal flux of a single phase 2-wire line, of a 3-phase 3-wire line with equal phase spacing, of composite conductors. The best example is a stranded conductor. Of unequal phase spacing, that is 3-phase 3-wire line, okay? And then of bundled conductors, and lastly of a 3-phase double circuit lines. Now, before arriving at the inductance of a more general type of conductor and other conductor configurations, the internal, external, and total inductance of a solid cylindrical conductor was first computed. So we'll just discuss the overview of how it is determined here, no? But as to the detailed derivation, it was provided to you through the reading activity. Alright? Okay, so the following parameters were obtained one by one in order to determine the inductance at the end. Okay, so first thing is magnetic flux intensity, which is determined from Ampere's law. And it is saying that the tangential component of the magnetic field intensity vector, H tan here, alright, in this equation, integrated along a closed path, which is dl here, equals the net current enclosed by that path. Alright, so from Ampere's law, they derived the H, okay, or the magnetic flux intensity H. Okay, and then after this integration, they use this H, alright, to get the magnetic flux density B, using this formula involving mu, alright, or the magnetic flux, the permeability of material, and then times H. And then afterwards, flux linkages are obtained, alright, and then finally, the inductance, alright, is determined by having this equation utilizing the lambda or the flux linkages determined. Alright, so the inductance here is lambda over I. Of course, there are also these assumptions, no, that they considered when inductance is obtained. One assumption is that the conductor is assumed to be sufficiently long, alright, as if we cannot see the end, something like that, such that the effect of that magnetic field at the end is negligible, okay, so that also in the end the effect of that end is no longer included in the calculation. Okay, now the second assumption is the conductor is non-magnetic. That is, its permeability is equal to permeability of free space, that is 4 pi times 10 to the negative 7. Okay, and then the last assumption is that the conductor has a uniform current density, so that the skin effect is now neglected. Okay, now moving on, the internal inductance, okay, that is due to the flux linkage inside the dashed contour here, is given by 1/2 times 10 to the negative 7th Henry per meter. And that is, yes, you can observe that to be a constant. There are no other parameters involved here. Okay, so that's the internal inductance. Okay, when we say internal inductance, it is the inductance that is due to the flux inside the conductor. And then we have the external inductance due to the flux linkages between P1, okay, which is outside the conductor already, and another P2 that is outside the conductor. Okay, so please take note of that, no? So those P1 and P2 points are outside the conductor, all right, already. And between P1 and P2, there is this external linkage, the linkage between P1 and P2. Okay, and the inductance, okay, due to those external fluxes or flux linkages is now 2 times 10 to the negative 7 ln of d2 over d1. Your d2 is the distance between P2 and the center of the conductor. Okay, please take note of that. As well as d1 is the distance between P1 and the center of the conductor. Okay, and now the total inductance due to both internal and external flux linkages. With this, you have to recall the previously derived inductances. Okay, one that is internal, LINT, and then L12, the external. Okay, so we're considering these points here. The external point P, which is at a distance from the center, at a distance T from the center of the conductor. Okay, so two flux linkages are considered here. The one that is brought upon by P, and the other one is the self flux, which is inside the conductor itself. Okay, now, so recalling your LINT and L12, now the total inductance, LP here is, what is LINT? That's 1/2 times 10 to the negative 7, and L12, or the external inductance, is 2 times 10 to the negative 7 ln of D over R. So previously it's D2, so in this case, we represented D2 here as D. Okay, and then yung D1 is now R. Okay, so simplifying by factoring out 1 times 10 to the negative 7 gives you this one. Okay, and then further simplification or factoring out 2 times 10 to the negative 7 will give us this parenthesis. Okay, 1/4 plus ln of dr. In this case, we just have to let that 1/4 is ln of e raised to 1/4. There is no difference between these two except that we factored in ln e, but they are just the same because ln e is 1, right? So 1/4 remains the same as 1/4. Okay, so applying this 1/4 equals ln e 1/4 to the parentheses will give you this, and simplifying the parentheses using the properties of natural logarithm ln, diba yung ln e 1/4 and then plus ln d over r will be simply combined as a product. So ln e 1/4 times d over r, and then eventually that 1/4 was transferred to the denominator. So naging negative 1/4. Okay? Alright. So, now, the total inductance becomes 2 times 10 to the negative 7 ln of d over r prime, wherein r prime is re raised to negative 1/4 or 0.7788 R. Okay, so that is for the internal inductance, external inductance, and then the total inductance that is due to both the flux linkages, internal and external. Okay, now we'll have the inductance of a single phase two-wire line. Okay, so consider this conductor 1 with the radius R1, R sub 1. Okay, and then we get its inductance first. Okay, but of course we have to consider the effect of the flux linkage brought upon by the conductor 2, okay, or another external conductor. Okay, so L1 here, or the inductance of this conductor 1, is 2 times 10 to the negative 7 ln of d over r1 prime. So if you may recall, so sinabi natin kanina that the total inductance due to both the internal and external. Ito yun. Okay? And then, for conductor 2, the same thing, no? So, conductor 2, inside and then outside of it is conductor 1. So, there are flux linkages between those two. So, we made use of the L12 formula a while ago. Okay? So, L2 here is, note that R sub 2 prime ang ginamit natin for the denominator. Okay? So, this L1 and L2, please take note that they are just inductances per conductor. Okay? And for a single phase two-wire line, we might also be interested to the total inductance of the entire single phase two-wire line. Okay, so that is your loop inductance, or the total inductance is L1 plus L2. And by simply adding L1 and L2 will give us 4 times 10 to the negative 7 ln of d all over the square root of R1 prime, R2 prime, Henry per meter. Now, if those two conductors have the same diameter or radius, okay, so simply your inductance is now 4 by 10 to the negative 7 ln of d over R prime. Okay, syempre when you simplify R1 prime equal to R1 prime din, di ba, yung R2 prime. So, R1 prime squared, squared. So, R1. Okay, which is also R. Kasi isa lang naman yung radius. Okay? So, we'll have the next inductance, which is inductance of a three-phase, three-wire line with equal phase spacing. But please do check out this discussion in another video. Okay?